How can the pipeline handle branch and jumps instructions? What could we do about that? Nothing? Nothing. Well, let's see what's going on. Branch if equal, which is in your simulator. Send target to PC if test is equal. So branch if equals 1 and 1. Fetch, decode, execute. Memory is when you actually evaluate the branch, but maybe a subtraction right afterwards is already into execute. We don't want that. We don't want the subtraction to happen because obviously we're taking the branch. So how can we do this? Well, what were the three options we had with data hazard? First one was the operating system's answer.
Ignore it.
Ignore the problem. What was the next one?
Install it.
Detect install. And then the last one is forward. But this time it's branches, so we're not going to forward. We're going to
jump.
We're going to predict. Predict. So let's go ahead and first do avoid, detect, install, speculate, and squash if wrong is the technical term.
Speculate and squash.
Right. So avoid, make sure there's no hazards in the code. All right. Detect, install. Delay fetch until the branch is resolved. Okay. Speculate and squash if wrong. Go ahead and fetch more instructions in case it is correct, but stop them if they shouldn't have been executed. So avoid all hazards. Don't have branch instructions. All right, who's ready to do this?
Problem solved.
All right. The actual other solution to this is called delay taking the branch. You would literally, and Spark did this, delayed branch if equals. What it would do is the two instructions after it will go ahead and be executed while that branch is in the pipeline. Okay? So that changes your architecture. I mean, that's fine. You just said the next two instructions are okay. Instruction PC +1, PC +2 will be executed before deciding whether to fetch from PC +1 plus offset. If no useful instructions can be placed, no ops are inserted. So what does this do?
Executes things you might not need to execute.
Hopefully this slide looks familiar. Your old programs need to be recompiled, and they probably will not run correctly on your new implementation. Longer pipelines need more instructions or no ops after the delayed. Programs get larger as no ops include, especially a problem for machines that try to do more instruction every cycle. Like remember Intel Epic with its bundles? Now it's going to have a lot of no ops. Program execution is slower. Your CPI is 1, but you have some no ops. Does this sound familiar? Yeah. All right. So is avoiding the problem a good one? Terrible. That's an operating system solution, not an architecture solution. Okay. Detect install. Well, this one's actually pretty easy. When you have a branch in decode, you basically say, okay, you issue that instruction, and then you just stall until that branch is resolved. And then you either jump to the next PC or not, and we're done. Okay. So, if it's a branch, you just keep doing some no ops here. Watch, no up, no up, no up, and then we're done. So let's go here. Wait. That's not telling me. What's saying is you branch, no up, no up, no up. Oh, it's resolved. Then you go and execute the next one. So every time there's a branch, what happens to your pipeline?
No up, no up, no up.
No up, no up. You get some no ups. And then your CPI increases for every branch. On average, there's one branch every 4 to 5 instructions. So that would be a lot of no ops. All right, we can do better than that. We either, basically, one thing about the beauty of control hazards is it's branch if equal. Namely, you're either taking it or you're not taking it. So if you want 50% accuracy, what do?
Guess.
Right. So by just guessing one or the other, you're probably 50% correct, which is actually pretty significant for predicting, right? That's pretty good. About half of the time branch is taken, so if you assume that it's not taken, we ignore the branch if equal, treat it like a no-op, and keep fetching. What if we are wrong? As long as we do not complete any of the instructions, we are okay. I.e., don't perform write back on any instructions that need to be squashed. But that's okay because all those instructions are behind the branch if equal, not in front of it. So, if we were wrong, then you squash all the instructions and you fetch again just like normal. And if you're right, you just go along your merry way. Okay? Speculate and squash. Assume, yeah, so that's what we're doing. We're speculating. Assume not equal, keep fetching. Stop bad instructions. Basically, you just send a no-op to decode and execute in memory. aka whenever you mispredict the branch, you stall for 3 cycles. And then you send the target to the PC and it restarts. We're doing good? It's a little complicated. So, branch if equals, oh no, we were wrong. No up, no up, no up. All right? And then since the PC plus 1 has been updated, the MUX has selected it, the next instruction will be correct. All right, that makes sense? That's what you do when you're wrong. CPI increases every time a branch is taken. That's if you're doing detect and stall. Obviously not. We can fetch from a target before even we know the previous instruction is a branch, much less whether it is taken. So here we go. What can we do here? Okay. All right. The question is, if the branch is taken, how do we know what the next PC is? It's
Branch, then it's
PC plus 1 plus offset. Okay. Unfortunately, that may take too long to actually execute circuit-wise to calculate that. So instead what we do is we store, once we say, oh wait, we're going to store this branch as being taken, we're going to then store the next address. So if we know that the PC is equal to a certain instruction, whatever the branch program counter was, if those two are equal, then we're going to send this target up to the MUX instead of PC plus 1. So we are having an array, an associative array, cache, down here that'll store what the targets are for certain branch PC counters. Now the target could be PC plus 1 plus offset. It could also be PC plus 1. But that's where the target's going to be stored. Y'all see why this is an issue? Because we can't just calculate PC plus 1 plus offset automatically sometimes. We have to figure out which one we want to move in. Because the offset's part of the instruction.
the BPC,
Branch program counter.
branch program counter.
So that was the program counter of the branch that we are predicting. So if we, for example, let's say we had a branch, at a PC 5, right? And it went through the pipeline and we found out, oh, it's taken. So we're going to store what the target was at that time here and then store the value 5 over here. That way, the next time the PC becomes 5, we know to just pull from this target register instead of going PC plus 1.
Okay.
Okay? So the branch has already been mispredicted once.
So that's not the offset BPC. That's just
No, BPC is the branch program counter. So
that's
for
where the program counter is at the branch.
yeah. So PC 0, 1, 2, 3, 4, 5, 6. Right?
That's
6. the PC would be 6 while executing this branch. So we would store 6 right here. That way when it's equal to the PC, we know to go to that target.
So would that be like if you came back to the 6?
Mhm.
Okay.
Yeah.
Because otherwise that's pretty worthless.
Yeah, well, you usually predict not taken because that's the easiest to predict at first. Just keep doing what you're doing. And then if you were wrong, then you fix it. All right, branch prediction. This is actually a very interesting field. So if you predict not taken, you're about 50% accurate. All right. That's not even implementing this. You just predict not taken and just keep going. PC plus 1 all the way, man. All the way.
That's what we're doing, right?
Backwards taken, it's actually 65% accurate. So in other words, if the address is previous, aka this offset is negative, you want to predict taken, otherwise not taken. Why does that increase to 65% accurate?
Because of the while.
Yeah, your loops, right? Most of your loops are going back. So this actually makes some sense. Yeah, it makes some sense. Yeah. Predict same as last time. You just store what all the values were in the past and just use the one that's last time. Okay, we're up to 80%. Actually, we're up to 80%. That's pretty good, right? I mean, we're actually able to predict it 80% of the time correctly. All right. The Pentium 1 is 85% accurate. Pentium Pro is 92% accurate. Do I have the latest ones up here? Best paper design is about 97% accurate, and that's usually around 95, 96 is where we are. So, wow, yeah.
Nerds.
Nerd. Why is it so important to be accurate?
Performance.
Performance. This is just 5 stages. Pipelines nowadays are between 20 and 40. So each time you're wrong, you're losing 20 cycles or something. You're losing a lot of time. You want to be accurate here. So this is very, very important. Okay. So detect, install, wait and decode. We already talked about that. That's great. Roll with the compiler. Wait, is this all we're going to talk about?
So we're doing that one.
Wow.
We're doing the detect install.
No, you have to use a G share, which I'm going to have to present on that, I guess, next time. I don't have these slides. That's frustrating.
Guess you're going to have to push that due date back to
Nope.
February 6th.
You've got plenty of work to do between now and next week on this. You can just, if you can get everything but branch prediction, just predict not taken for now, and you're fine. Yeah. All right. So I'm going to have to go and find out what happened to my branch slides, but I'm going to take a quick step back and talk about the role of compiler in here. You think about the architect has to interface with the compiler writer a lot. So the compiler is the primary user of the instruction sets because the compiler is what generates all your instructions that the architect has to execute. Some device drivers still have instructions that are written by hand, but that's pretty rare. Some small embedded systems are written in assembly by hand, but that's also pretty rare nowadays as well. So the compiler is really the one that uses the ISA the most, the instruction set architecture that we have been developing. So it's to generate the correct translation. It should be fast compile time and generate fast code. While we're at it, make it a reasonable code size and some good debugging support, right? You might as well throw that in. Okay, so the compiler actually has a lot of work to do. Did you have to take a compiler's course when you were in? Okay, so you remember the front end and the back end?
Remember? Yeah.
So the front end translates your English-like code into some type of intermediate structure that makes sense to a compiler. And then the back end translates that intermediate form into the actual assembly code. we're on the architecture side. We only can care about the optimizations that can happen. The compiler does all this for us, and whatever. Cool. For example, the compiler does a lot of things, and this is good to touch base on. So common sub-expression elimination. C equals array 1 sub d plus e divided by array 2 d plus e. Do you have to do this add twice? No. Just add it once and put it in there. Very common for the compiler to do. You get rid of an instruction. Obviously, this is a very long equation. Again, you can just automatically do it, automatically fix it. What's the problem here? You have more register pressure because now you need to have a register for this I to store that temporary value in. Loop invariant, code motion. T equals 5, does that need to be executed every time inside the for loop? No, that can just be moved right up. Remove statements from loops that only need to be executed one. Idempotent. This actually pops up a lot because it's hard for the programmer to actually see some of these things. It is. Again, more register pressure because you're adding temporary into the registers. Okay, there's a bunch of other things. Inlining. Basically, take the function and you copy and paste it into the code without having to do a function call. Loop unrolling, you execute multiple iterations of the loop inside the loop before you do another loop, sorry. Software pipelining, another type of loop scheduling, and global optimizations. You notice here, greater code size, more register pressure. When I say register pressure, that means the compiler writer wants to use more and more registers to store all these temporary values. Oh, and why is that an issue for us?
We only have so many registers.
Only so many registers. Why don't we just increase the register file?
Or you have to keep up with when you
Way more we'd have to keep up with.
forecasting.
Yep. Yeah, that just makes it harder on us when we increase the register file. But that's what the compiler writers want. For example, when Linux went from 32-bit to 64-bit, the old 32-bit code, people would just, one of the big changes from 32-bit to 64 is 32-bit x86 had 8 registers, 64-bit x86 has 16 registers. So people would take 32-bit code, recompile it with the compiler, it would run on 64-bit, it's the same piece of code, and they would see about 65% performance improvement just because they could access more registers. So more registers definitely can help improve the speed of your program as long as your architecture can support it. But it makes it harder on us. Also, big is slow, small is fast, so the bigger you make the register file, the slower it is. Optimized code has different characteristics than unoptimized, right? Fewer memory references are in optimized code because the easy ones are eliminated. Memory is very, very slow and very slow, so they try and optimize those away as much as possible. And of course, remove redundant memory and ALU operations. So the compiler wants more resources for better optimization trade-offs, but we don't like that. We want same behavior for all contexts, even special cases. That can be somewhat difficult. Let's see, data independent of addressing mode, addressing independent of operation perform. Keep the instructions simple. It's easier to compose than fix. Okay. So MMX, one cool thing they did is right up here we have, add, right? What they did with MMX, because it targets video, and if you remember, video has red, green, blue, alpha. So what they would do is they would have one instruction that would actually add all those 4 values at once. So you could do 4 adds with one instruction. So for those adds, you had a performance improvement because you could do multiple adds. But that makes the compiler's job a little harder because now they need to know, do I use regular instructions or MMX instructions? That's what this slide's trying to tell you. So from an architecture standpoint, we're like, yeah, we'll give you a special instruction for that. And the compiler's like, okay, well, that makes my job harder, although I can do it and increase the performance of your code. The point here is the compiler writer and the computer architecture are at arms a lot about what to do, because what they want is usually the exact opposite of each other, what each other wants. Because we just want simple instructions. We don't want something complex. We want small structures. We don't want large register files or large memories. Small data bus fan out. We did Verilog. We don't want it to fan out a lot because that makes it hard to do layout. Very small instructions. We don't want complex instructions like MMX because that makes it annoying, but that's what helps with performance. So, to make processors faster, to make the compiler team happy, more aggressive optimizations for the entire program, more resource constraints, caches, hardware schedulers, and higher expectations, right? To make us hardware people happy, tighter design. So we want the clock to be as fast as possible. We want, execute optimized code, more complex execution, and make all stages the bottleneck. So you remember at the beginning I had different numbers. We want every stage to be very, very close timing-wise in order to make our processors as fast as possible. Okay. Good. We did this in about 2 hours. Beautiful. That is all I'm going to present for today. I'll need to go over branch prediction. And I did give you one book homework. Let me go ahead and at least, I'm going to give you an extra week for that book homework because it's going to be difficult, and I'll go over that momentarily.